session 5 for the model 4 of the response spectrum topic. In this session you will going to see about the numerical evaluation response of single degree of a freedom system. So here there are two basic approaches for the numerically evaluation of the dynamic responses. The first approach is that numerical interpolation of the excitation, and second one is the numerical integration of the equations of the motion. Both the approaches are applicable to linear systems, but the second, whatever the approach is there, it is related with the non-linear solutions are concerned. Now the analytical solution is usually sometimes not possible when excitation varies arbitrarily with the time, or if the system is non-linear. Under such problem and can be solved by the numerical time stepping method or for the integration of differential equations, and that is to be known by the time stepping method. So this time stepping method, here let us take the equation whatever it is to be solved. So it is the linearly elastic system. You can see that here the equation, and second one is for the inelastic system. So inelastic system, so we are concerned with the linear elastic system only, not for the second one. So here the initial conditions are there, whatever the u naught is nothing but initial displacement, you can call it is a u naught, and u dot is a velocity at 0 second is u dot. Now here let us apply the force whatever it is there for the set of the equations like pi is equal to p of ti. So here the whatever the interval will be there from 0 to 1, 0 to I is 0 to 1, that is the time interval is delta ti is equal to ti plus 1 minus I. Whatever the response is there is determined as a discrete time instant, whatever the ti is there, the displacement and velocity and accelerations at ti is denoted by, this is ui is the displacement, ui dot is velocity, and u double dot is nothing but the acceleration respectively, are assumed to be known as the satisfying this equation. This one is a basic dynamic equation, mu dot plus cu dot plus ku at I interval is equal to pi. Now the whatever the numerical procedure is there to be presented, which will be enabled to determine the responses. Next response, that is ui1, u dot I plus 1, I as well as u double dot I plus 1 at the I plus 1 interval. So that is to be again written as the basic equation. You can see it here, whatever the horizontal it one is there t, and the vertical is p ordinate is there, and below that horizontal is t, and displacement. The first one is the force, how the force is going to vary, correspondingly the displacement is going to vary. At t is equal to 0, p naught is the initial force, u naught is a displacement is 0, because at t is equal to 0, as the time is going to increase, the displacement will be either increase decrease depending upon the force. You can see that t1 p1 is there, u1 at t1 is there, t2 u2 is there. So like that the total, the whatever the force in incremental is delta ti, means the small interval, and similarly displacement is going to take place from ui to ui1. So means it is to whatever the figure is there. So figure whatever it is represent is nothing but the time stepping method, step by step whatever it is there. So here this is the way how this notations are given with respect to the how force and how the displacement is going to takes place. And now here the whatever the representations at the time ti at I plus 1 to be determined from the response at the time I is usually not exact. Many approximate procedures are numerically possible, the requirement for the numerical procedures are, first one is the convergent. What it says that the numerical solution should approach the exact solution as the time step is decreases, and the second one is the stability. That is, the numerical solution should be stable even if there is some round of error or approximation is there. Then third one is their accuracy. The numerical solutions provide the results that are close to the exact solution. So like that the numerical procedures are to be seen. These issues are very important in numerical methods for solving the equations. They will govern the whatever the limitations of the time stepping procedures are there. So whatever the three types of the time stepping procedures are there. The first one is the method based on interpolation of excitation. The second one is method based on finite difference expression of velocity and acceleration. Then third one is method based on assumed variations of acceleration. So we are going to consider this third one for the present study, and that one is to be well known by this method as called as Newmark beta function. Newmark beta function. So that is Newmark method is given by this equations. The velocity as well as this acceleration. The velocity is given as u dot I plus 1 is equal to initial whatever the velocity plus the incremental whatever the incremental. So here gamma and beta and gamma functions are there. So gamma is 0.5 according to the Newmark method. The gamma is 0.5, whereas beta is varying from 1.6 to 1.4, 1.6 to 1.4. So this is all about these two whatever the Newmark whatever the mathematician was there, which he proposed his method in 1959 only. Okay, whatever the parameters beta and gamma are there, they define the variations of accelerations over a time step and also determine the stability and accuracy characteristics of the method. Okay, so now as far as the special cases are concerned, so we'll have these special cases. The first one is the average acceleration, another one is linear acceleration. So we are talking about the linear acceleration only. We are talking about the linear acceleration, and average acceleration here the gamma will be half, beta will be 1/4, whereas in the linear acceleration beta is 1/6, gamma is half, means only beta is going to vary. When the beta is become 1.6 of the Newmark method, then we'll call that one is the linear whatever the linear acceleration. And also here it is the whatever the time steps are there, ui to ui double 1 is there, and here it is linearly it is varying, whereas in the linear acceleration it is varying linearly. So you can see that in the figure, average acceleration, linear acceleration, average acceleration ui and ui plus 1. So here it is a average, and whereas in the linear, so ui1 to ui1 ui plus 1 is varying linearly, so that inclination linear is there, and that is for the time interval of delta t. So both the whatever the acceleration component where the whatever the beta and gamma functions are there, so we can see the all these the different steps how this the first is average method, another one is the linear acceleration method. Let us see the linear acceleration method. So in the linear acceleration method, whatever the acceleration is there with incremental you can see that incremental I2, then linearly it is varying, means 2 divided by delta t. So it is a difference of ui double dot I plus 1 minus ui, how it is linearly going, that in between anywhere you want. Yes, then the corresponding velocities, and this velocity is further simplified, and again velocity to displacement. So this displacement equation at the end, ui plus 1, so is nothing but ui plus ui dot delta t plus delta t square into 1/6, whatever the value of the beta is there, 1/6 is there, and whereas here it is a 1/4, that is the difference of this particular linear equation how the displacement is to be calculated. So you can see that the average acceleration method, gamma is half, beta is 1 by 4, and in linear beta is equal to 1 by 6, whereas gamma is remain 1 by. So here how this the procedure is to be carried out. So here the steps is given, the initial calculations for the initial acceleration, how this initial acceleration is to be calculated. So this initial acceleration is calculated as p naught minus c into u naught minus k into u naught divided by m is there. So now select the some time interval. So now the whatever the k dash or k cap is equal to, or next k is equal to k plus this particular equation, and a then b c are the constant. Then next the whatever the time steps are there, next incremental is to be calculated like that. So here whatever the finally we are interested about the displacement, that is 2.5, here it is given displacement at next displacement, next velocity and next acceleration. So now like that the cycle is to be repeated by I plus 1, whatever 2.1 is there, 2.1 to 2.4, 2.5, these are the initial condition, these are the a calculation step. 2.1 to 2.5 is the calculation steps. So like that the variations for the different steps of I means next step, like that these is to be calculated. This is the way how this. Now here we can have the some the conclusions that Newmark method is a stable if the delta by t is equal to less than or is equal to 1 by pi omega 1 by pi into square root of 2 into 1 by square root of gamma minus 2 beta. So here for the average acceleration you will have the gamma, for linear acceleration gamma and beta are like that. So delta by t here for the average acceleration is infinite, and whereas it is 0.551. So like that is there. So this is the way how this the requirement of linear and as well as the average we have seen, but here for the present study is related with the linear only. The requirement is not significant because much smaller time step required for the accurate representation of excitation and response is there. So now we'll continue. Here in this case is a earthquake response spectrum. So here the next topic in this session is the response spectrum. So what is a response spectrum? Response spectrum is simply a plot of peak response. What are the peak response are there? Displacement is a one response, velocity is another response, and acceleration is also another response of a what? Of a number of single degree of freedom system which varying with the natural period and that are forced into motion by the same base variation. The resulting plot can be used to find the response of any structure with knowing the natural period. So this is all about the response spectrum is there. What is the advantage of the response spectrum? This response spectrum has found the very important in the structural engineering, since it inceptions of the response spectrum method, the analysis find the advantages like the whatever the pseudostatic analysis, it consider the frequency effect, and through the dynamic analysis it provide a single suitable horizontal force for the design of structure. Then the idealization of the whatever treating of the system as a single degree of freedom is acceptable in a structural engineering problems where the complexities are involved in terms of geometry, material properties and boundary conditions are relatively less. So this is all about the how this what is the response spectrum and what are the advantages of response spectrum. Then how this response spectrum is to be constructed. The response spectrum may be expressed as I told you that it is in terms of acceleration versus time, or velocity versus time, or displacement versus time is concerned. Whatever the maximum values of each of these parameters depends only on the natural period, means whatever the natural period of a single degree of freedom system, or natural period or a frequency, and also the damping ratio of a single degree of freedom of a system. The maximum magnitude of the acceleration, velocity, okay, so and the displacement at different natural periods are referred as the spectral acceleration. It is called as SE, spectral acceleration, spectral velocity, and spectral displacement, because it is a response spectrum maximum ordinates are there. So that's why it is called as acceleration is from the spectra. Spectrum is the diagram or a figure from which we got it. SA, SV means the pseudo velocity, spectral velocity, as well as the spectral displacement, SD, like that. A single degree of freedom system of zero natural period means infinite natural frequency would be a rigid, and its spectral acceleration would be equal to the peak ground accelerations are concerned. Now the maximum response motion, the whatever the of acceleration, velocity, and the displacement at different natural periods, which are referred as a the SA, SV, and SD is there. Now here a single degree, whatever the single degree of a system, that is the zero, whatever it is there. So in that cases we can take it as a infinite natural frequency. Okay, and also the maximum response motions of the spectral acceleration, like velocities, displacement, can be approximately related with the some expression. So here the spectral displacement SD is equal to whatever displacement maximum is there. Then spectral velocity means whatever the velocity is maximum. Spectral acceleration means whatever the acceleration is maximum with these relations. Pseudo and the velocity and accelerations can be related with pseudo, the whatever the velocity is there, nothing but omega n times of the pseudo displacement, whereas acceleration is equal to omega n square times of pseudo displacement. If you know the displacement and the velocity, natural frequency, so that we can find out pseudo acceleration as well as pseudo velocity. Like that we can have the relations between the pseudo velocity to displacement as well as pseudo acceleration to displacement. Since the whatever the peak ground acceleration, velocity, displacement for the various earthquake record differs, the whatever the computed response cannot be averaged on a absolute basis. Hence normalized is carried out by dividing the spectral ordinates by the peak ground acceleration, velocity, and displacement for the corresponding region of the spectrum. And the earthquake parameters such as soil conditions, epicentral distance, and magnitude of the earthquake, duration, then the source characters influence the shape and amplitude of the response spectrum. While the effect of some parameters may be studied independently, the whatever the influence of the several the factors are to be interrelated, and it is difficult to consider individually. So here you can see that how this response spectrum is to be constructed. We can see that this is a one story building whose peak is different, and that one is identified here. So he can see that above the figure natural period versus spectral acceleration is there, whatever the maximum acceleration is there, ground acceleration. You can see that ground input is ground accelerated. Another type of building, again the peak will be different. Another type of the building, its peak will be different. Next, that peak will be different, and next the peak will be different. Then plotting up all the peaks of different natural period, whatever the single story will find it, every single story the height is going to vary, means the period is going to vary. Then according to that its peak response is also going to vary, peak acceleration. So that joining the all the points of individual periods peaks, that is called as the response spectrum. Now you can see that how this response spectrum is developed. In order to explain the procedure for the development of the design of a spectrum chart, a typical time history accelerations with the 2% damping may be considered. Okay, so whatever the 2% damping is considered, you can see that 2% is there, time period damping 2% is there. You can see that 2% for the different the time period. So the first time period is 0.5 second is there, 1 second is there, 2 second is there. According to that the deformations can be plotted. Then for the different natural periods, the Tn of the system, the peak displacement were obtained from time history plot. Then the peak displacement so determined for each system provides the 1 point on the deformation response spectra. Then the complete deformation response spectrum plot for the 2% is here it is presented. Then each of the deformation, the pseudo velocity, pseudo acceleration spectra for a given ground motion contain the same information. Then the deformation spectrum provide the what? Peak deformation of the system. Then the whatever the pseudo velocity spectrum is related with the peak strain energy stored in the system, whatever the peak strain energy stored in the system of the earthquake. Then the pseudo acceleration spectrum is related with the peak value which is equivalent to static force and base shear. Thus the whatever it is combined is there, it's a useful. Then whatever the three charts are there, you can see that three combined DVA graph for displacement, velocity, acceleration. D means displacement, V means velocity, A means acceleration. DVA spectrum, okay, with the damping ratio of 2%. You can see that 2% is the damping ratio. Whatever it is there, three charts are to be combined. What are the three charts? Displacement is also combined. You can see that the time is the time period, Tn is the base, vertical velocity is there, one diagonal represent the what? Acceleration is there, another diagram is represent the displacement is there. So whatever the three charts are there combined together in a single chart with a log scale. You can see that the time period is also log scale, velocity is also log scale, acceleration is also log scale, displacement is also log scale. So all these are log scale only. The scales of dA, whatever they are there, displacement and acceleration are, they are sloping 45 degree to the x-axis. You can see that the displacement 45 degree, acceleration minus 45 degree. Okay, so like that. Since the peak ground acceleration, velocity and displacement for the various earthquake records differ, the computed response can be averaged on the absolute basis of normalization is carried out by dividing the spectral ordinates by the peak ground accelerations, velocity and displacement for the corresponding region of the this one. So now here it is a 2% chart is a tripartite chart is there. It is also called as tripartite. Three parts are there. Okay, if you know the time period and if you know the velocity, so other things can be easily plotted. If you take the perpendicular to that one, acceleration can be counted perpendicular to that one, you will get the displacement. Like that, if any two things are known, other two can be calculated. This is all about tripartite. And the properties of the tripartite is that the initial is very active in the acceleration, even small time period the acceleration is more. As the time goes here, so acceleration is reducing, whereas this displacement initially it is less, but as it is time, time period is increases, displacement is increased. So that's why here it will be three parts will be there. The first part is acceleration sensitivity, the second part is velocity sensitivity, the third part is displacement sensitivity. So the sensitivity of the diagram can be seen here. So that is all about the tripartite or a DVA spectrum is concerned. Now the next part is elastic design spectrum. So the design spectrum should satisfy the certain requirement as it is initiated for the design of new structures. That is, the response spectrum for the ground motion recorded during the past earthquake is inappropriate. Then the response spectrum for all the different motion is also uneven or a zigzag. Thus the design spectrum should consist of smooth curves or a series of straight lines with one curve each of having certain damping. Generally, as a compromise, the different ground motions are considered as response spectrum is developed. The designed response spectrum is based on the static analysis of the response spectrum for the particular ground motions. Then each ground motion is normalized and scale up or down so that all the ground motions are with the same peak ground acceleration. The response spectrum of each normalized ground motion is considered. Then the whatever the each ground motion is normalized either scale up or scale down. Now the response spectrum, whatever it is there, so the mean values of the spectral ordinate for the each period are obtained. Then statistical analysis of these data provide the probability distributions for the spectral ordinate. Then the obtain the coefficient of variation is equal to standard deviation plus mean. The whatever the connecting all the points of mean response spectrum is and the mean the whatever the standard deviations of the response spectrum there are the smoother. Then the idealization of the series of straight lines. Then finally we will arrive the elastic design spectrum. So now you can see it here, the final whatever the smoothened graph of the response spectrum from the code book, that is IS 1893-2006. There are two response spectrum is there. One is SA by G versus time period for the equivalent static method. Below that one more is SA by G versus the time period or natural period. That is the response spectrum for the spectra for the response spectrum method. The two methods are there. One is static method and the one is response spectrum method. Two methods are there for the design response spectrum, whatever it is available in the IS 1893-2016. There are three spectrum also. There are three types of the soil condition is there. First, the third one is there. Thin line is there, soft soil, then medium soil, then dark line is the rock. Similarly, same thing is applicable for the spectrum method. Like that, the response spectrum which is also available in the IS code, that is IS 1893-2006, you will get two response spectrums. Okay, so based on that, some numerical examples also to be studied in the next model. Okay, this is all about the response spectrum. In this case, we have seen that the numerical evaluation, how it is to be done using the time step method, that is linear acceleration method, using the numeric beta function, and also we have seen the concept of response spectrum, construction of the response spectrum, as well as how this tripartite or the how the three parts are to be included in one, and also the design of the response spectrum, elastic design of response spectrum, and how one can see the whatever the codal provision which is available in the 1893 codal provision also we have seen. So this is all about the whatever the response spectrum topic is concerned.